Hello everyone and welcome back. My name is Mr. Koval, and in this video we're going to go over a couple of examples of how to fill in your orbital diagram for the molecular orbitals of some homonuclear diatomic molecules. So let's get into this. So the first question we have, or the first problem is, it says to use a qualitative molecular orbital energy diagram or energy level diagram to predict the electron configuration, the bond order, and the number of unpaired electrons in the sulfur to the S2 molecule, a bright blue gas at high temperatures. So, first thing we need to figure out is the ordering of the molecular orbitals. So, remember what I said in the previous video. Um, we have to determine, is our sigma pz molecular orbital, the bonding molecular orbital, is that going to be lower than the pi spx spy, or I should say not spy, but NPX or NPY pi molecular orbitals, because this is going to depend on the energy gap between the S and the P orbitals, the atomic orbitals. So if you remember from before that, as you go across the periodic table, right, from left to right, the effective nuclear charge is getting bigger, right? So the nucleus is becoming more positive. That's going to cause the difference in energy between the S and the P orbitals to grow. And so you're going to have this sigma PZ molecular orbital, that's going to end up being lower than your pi PY PX molecular orbitals as you go across the periodic table. So we saw that with oxygen and fluorine, this orbital, the sigma orbital, is going to be lower in energy than the pi px py molecular orbitals because of that increase in the energy difference between the p's and the s orbitals, the atomic orbitals. But if you are earlier on, if you're further to the left of the periodic table in your period, then these two will be switched. But since we're dealing with sulfur, the sulfur diatomic molecule, sulfur is right under oxygen. So we saw that with oxygen, we would use this ordering of the molecular orbitals because oxygen and fluorine are far to the right of the periodic table. So this this is going to be the order that we would use since sulfur is also underneath oxygen. Then we would expect this to be the same order for the same reason. So now that we have that taken care of, we're going to be using this energy, molecular orbital energy level diagram. And so the next thing is just to fill it in. So sulfur, because it's under oxygen, has 6 valence electrons because it's in group 6, just like oxygen. So we should fill in each of our sulfurs with 6 valence electrons, following the rules and the principles, right? So Aufbau principle, we're starting low. So we're going to fill in 2 electrons there, spin up, spin down, following the Pauli exclusion principle. Now we're going to fill in these 3 degenerate p orbitals, one at a time, following Hund's rule. So we've got 4 more electrons. So we're going to go 1, 2, 3, and then 4. And then it's going to look the same on this side as well. So 1, 2, 3, 4, 5, and 6. Since we have 6 on this side and we have 6 on this side, then we have 12 total electrons that we could fill in the molecular orbitals with. And we're going to follow the same rules and the same principle. The Aufbau principle, starting at the lowest energies, working our way up. So spin up, spin down. Go to the next energy level, fill that one up, spin down. And then the next one, spin up, spin down. So that's 6. We got 6 more. Now we're going to fill these two in one at a time following Hund's rule. So 1, 2, both spin up. Now we're going to pair them up, spin down, spin down. That is now 10 electrons. We got 2 more. They're going to go to the next energy level. And again, these are equal energy. So following Hund's rule, one at a time, both spin up. 1, 2. And that is all of our electrons. So we filled it in 12 electrons. Now we can start to answer the questions. First is the electron configuration. So just like with your atomic orbitals, when you're writing the electron configuration for the atomic orbitals, we can do the same thing for the molecular orbitals. So for S2, we're going to just write the electron configuration starting from the bottom and working our way up. So we got the sigma 3s orbital. So we got 2 electrons in there. So we'll write sigma 3s with 2 electrons in that orbital. Next, we have the sigma 3s star. So the sigma 3s star antibonding orbital, that has 2 electrons in it. Next, we have the sigma 3pz. So then next would be the sigma 3pz bonding orbital, that has 2 electrons in it. And then next we have the px and the py. They're the same energy, same level. So we're going to put those electrons together just like we would with the p sublevel. So we're just going to write this as pi 3p x and y. And that's going to have a total of 4 electrons because we got 2 there and 2 there. And finally, we have 2 up here. So that's going to be the antibonding orbital. So that's going to be pi 3p x and y. And then we got the star. And we got 2 electrons in there. So that would be, so this would be the electron configuration for S2. Okay, what about bond order? So again, bond order is simple to calculate. We're using our equation. Bond order, BO, not body odor, bond order. So what is that equal to? It's the number of bonding electrons minus the number of anti-bonding electrons divided by 2. That difference divided by 2. So we have anything that does not have a star is bonding. So we got 2. We have 2 there. That's 4, 6, and 8. So we got 8 bonding electrons, and then anti-bonding is anything with a star. So we have 2 here, and then we have 1 and 2 there. That's 4. And then that's going to be divided by 2. So 8 minus 4 is 4 divided by 2. 4 divided by 2 is 2. So that gives us a bond order of 2, meaning that there is a double bond between the 2 sulfurs in the molecule S2. So again, just like oxygen. So we would expect the same thing, because why? Oxygen and sulfur are in the same group, same family on the periodic table. So we would expect them to have the same characteristics, right? And so far, so good. And now what about, what was the other thing? The number of unpaired electrons. So that's really easy. We just look at our orbital diagram. We have 1 and 2. So we have 2 unpaired electrons. That tells us that S2, if we were to predict the properties of S2, we would say that it must have magnetic characters because it's got those unpaired electrons. And so they're all spin up. They have magnetic properties. And so you would think that S2 would react to magnets if you were to put magnets around or near the S2. And so just like oxygen, when it's in the gases or liquid oxygen can be suspended between two magnets, you would expect the same thing with sulfur. Okay, so I forgot to write down here that this would be the S2 molecular orbitals. So we got the molecular orbitals in the middle, we got the atomic orbitals on the sides. So that, ladies and gentlemen, is how you answer this question with regard to S2. Let's go on to the next problem. Stay tuned. Okay, so next problem, basically everything is the same. It says use a qualitative molecular orbital energy diagram to predict the electron configuration, one, the bond order, and the number of unpaired electrons in O2 to minus ion. Okay, forget the bright blue gas. I forgot to erase that for our new problem. Okay, so it's the same. First thing, figure out what molecular orbital energy level diagram you need. Since oxygen and sulfur are in the same category, we can be sure that we're going to use the same ordering of the orbital diagrams of the molecular orbitals. Again, because oxygen is far to the right, and so you're going to have a larger nuclear charge that's going to cause the S and P atomic orbitals to be larger, a larger difference in energy between the S and the P orbitals. And so this is going to be the ordering of the molecular orbitals. So next thing is fill in the atomic orbitals with your valence electrons and then fill in the molecular orbitals. So oxygen, again, is in group 6. However, it's got a 2 minus charge. So for the 2 minus charge, we're going to assume that we have two oxygen atoms or ions bonded together, so we can split up the charge. So we'll think, okay, we're going to have an oxygen ion with a minus charge on this side, an oxygen ion with a minus charge on this side, and then in the middle here we'll have the O2 to minus. And so remember, oxygen is in group 6, so it's going to have 6 valence electrons, but we got an extra negative charge. That means we have an extra electron, so that's going to be a 1 extra electron added, so that's going to be 7 electrons total. So we're going to have 7 electrons on both sides. So let's fill that in from the bottom to the top. So spin up, spin down, so that's full. So we got 5 electrons left, so we're going to go 1, 2, 3, following Hund's rule, and then we got 5 more. So we pair these up, spin down. Same thing over on this side. So it's going to be spin up, spin down, spin up, spin up, spin up, spin down, spin down. Okay, so now that we have our electrons, we got 7 on each side, so that's 14. We're going to fill in the orbital diagram. Notice that I changed the numbers to 2 because we're in the second period. So we're using the 2p orbitals, not the 3p orbitals like we did in sulfur, because sulfur is in period 3. So we're using the 3p's and the 3s and not the 2p's. So this for oxygen is going to be the 2s and the 2p's. So we got 14 electrons. We're going to fill in the orbital diagram, the molecular orbital diagrams. So we're going to do spin up, spin down, spin up, spin down. Next, we have the sigma 2pz, so that's going to be spin up, spin down. Now we're going to fill these in, spin up, spin up. Hund's rule, got to follow Hund's rule. And then spin down, spin down. So that's 2, 4, 6, 8, 10. So far, we got 14 left. or sorry, 4 left. So this is going to be spin up, spin up. We got 2 more. Now spin down, spin down. Oops. Sorry about that. Okay, so now we have that filled in. So now we can go ahead and do the electron configuration, bond order, and unpaired electrons. So first, the electron configuration. Again, we can write that using our orbital diagrams, using our orbital molecular orbitals, and work our way up like so. So here we're going to have O2, 2 minus. So we have 2 electrons in the sigma 2s. So we're going to have sigma 2s, 2 electrons, followed by the sigma 2s star with 2 electrons. So it's going to be sigma 2s star with 2 electrons. Next, we have sigma 2pz that has 2 electrons. So we're going to put in sigma 2pz with 2 electrons. Next, we have the pi 2px 2py that has 4 electrons for both of those. So we'll do pi, oops, I forgot the 2. So 2px and y, that's got 4 electrons in it. And finally, we got the anti-bonding molecular orbitals, pi, 2pxy, and z, x star. I'm getting tongue-tied. So here we have the pi with the 2p, x, and y. And that's going to be star because that's anti-bonding molecular orbitals. And there's 4 electrons there. Okay, so there is our electron configuration for the O2 2 minus ion. Next, bond order. Again, bond order is equal to anti-bond or bonding electrons minus anti-bonding electrons divided by 2. So the number of bonding electrons, again, those without the star. So 1, 2, skip, 3, 4, no star. 3, 4, 5, 6, 7, and 8. So that's 8. Bonding electrons, now the ones with the stars. So that's 2, 3, 4, 5, 6. So 8 minus 6, and that's going to be divided by 2. 8 minus 6 is 2, so that's 2 divided by 2, which gives us 1. So here the bond order is 1, which means that there is 1 bond between the 2 oxygens. So it's a single bonded oxygen molecule with a single bond. The 2 oxygens are bonded together with 1 bond. And so that's going to be a weaker bond than the normal oxygen molecule that doesn't have a charge on it. And then finally, the number of paired unpaired electrons. So you'll notice here that this has no unpaired electrons. So we would predict that O2 2 minus does not have magnetic properties. It's diatomic, or I'm sorry, not diatomic, sorry, magnetic, not paramagnetic. So we would not expect this to have magnetic properties. And so that's it for this video. I hope you found these examples very helpful. I hope you found this video helpful and entertaining and whatnot. If you did, then by all means, like the video, share the video, hit that like button somewhere over here. You'll find it. It's easy to find. Also, make sure that you subscribe to my channel. Do me a solid here. Hit that notification bell up there somewhere. When you do, make sure you click all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or question or a topic you need help with, I would love to do that for you. Thanks for joining me, and have a great day.